the summing up. I think today I want to do two things, if time allows. The first thing I want to do with you guys is to take it from here and lead to some very exciting and relatively recent results in statistical mechanics that I briefly mentioned in the past. And by recent, I mean last 20 years, considering how mature statistical mechanics is. The fact that these results have only 20 years is quite of impressive. And these are called fluctuation theorems. Now, as a matter of fact, most of the statistical mechanics that I will discuss in the next month or so is basically all very recent. It's all started after or at the dawn of the new century. So in particular, the fluctuation theorem that I'm going to discuss today, I think it's 1999. I had already began my PhD work at that time when these results came out, which is, say, half of a career life, considering my age. So in this sense, they're very recent. So what are fluctuation theorems? Well, when we refer to fluctuation theorems, we typically in statistical mechanics refer to two closely related theorems of statistical mechanics, devised by Jarzynski and by Crookes. As we shall see today, we're going to concentrate on Crookes, which is maybe a couple of months, came out a couple of months later than Jarzynski. And the reason we're going to concentrate on Crookes is that Crookes is a generalization of Jarzynski that gives Jarzynski as a special case. So by proving Crookes' theorem, you get Jarzynski for free. So as far as the proof goes, we will concentrate to Crookes and derive Jarzynski as a corollary. Although historically, Jarzynski was probably, if I'm not mistaken, I might be mistaken, but if I remember well from my days, Jarzynski should have started, should be a little bit earlier in terms of a few months earlier. Anyway, what do these theorems say? Okay, let's start with Jarzynski. Jarzynski imagines a process like this. You have a system in an initial configuration, which can be a thermodynamic state rather than just a configuration. But let this state be defined by, you have a system of which we can control some variable, lambda, for instance, is externally. And I want to go directly an example of what do I mean by that. So typically what people can do since a few decades, couple of decades, is to manipulate single molecules. So what is single molecule manipulation? I'm going to describe now an experiment, which is just one particular example of a phenomenological setup that is representing the theory that I'm going to discuss. So I will go theory and experiment hand in hand to show you that these very abstract results have a very, very physical, clear, tangible realization. So take a molecule of DNA or RNA, let's say DNA. Of course, it's a double helix, or you can take a protein. Historically, people started with DNA and then used protein. But let's say we have a DNA, let's say you have a protein, it's in a native state. So what people do, they express this protein using bacteria, and then they covalently attach to the endpoints some DNA handle. So basically here starts a handle of DNA. And at the end of which, for instance, you can put the gold nanoparticles. So let me draw with a different color my protein. That is the system that people wants to study. This represents the protein chain in a native state. Now, what people can do, they can measure with angstrom resolution this distance. There are many ways to do that. One way is to use optical tweezers or atomic force microscopy or magnetic tweezers. So basically, they're able not only to measure the distance between the gold particles, but also to exert external force with piconewton strength to the external particle, pulling apart these two particles, basically exerting a force. Well, in atomic force microscopy, they do something slightly different. They attach the protein to a point, then they have a pin, and then they pull back the pin like pretty much like a vinyl. You know the vinyl LP player, you know, where probably your parents used to use that, or your grandparents, I don't know. I have a collection of them. Like, so how does this work? So basically in this case, you have the tip of the reader bouncing all over and basically changing distance from the plate. And by doing this, they record an acoustic signal that is then turned into amplified and becomes a signal, right? So the information about the sound is encoded in the distance, in the modulation of the distance on the plate. Now, something like that is an atomic force microscopy experiment, where you have, you can measure very accurately the endpoint between the two handles. Now, for instance, one thing you can do is you can change the endpoints according to a schedule. Lambda, let's lambda be the endpoint. And I can change it according to a schedule by applying a force. Or I can change the strength of the force. This is just an example of a thermodynamic transformation that I can do according to a schedule that I decide. Maybe I decide that I stretch completely the endpoints until I reach the maximal extension of my chain in some couple of seconds, or maybe half a second, or maybe a millisecond. Okay? Now, clearly, if I do this process very, 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 very slowly, what is technically called adiabatically, I can assume that my system is always in equilibrium in a state determined by the external force and the system, right? And so, as we will see in a moment, it should not surprise you that I can put into a relationship the work done to stretch adiabatically the system with a change in Helmholtz free energy, right? Because you guys know this is standard thermodynamics. So basically, in this case, in general terms, the average, so when I'm in equilibrium condition, the system performs an adiabatic transformation. The entropy change is 0. Dissipated entropy, the entropy production is 0 of the universe. And therefore, all of my work goes in free energy change, right? However, when I have a finite realization, so when my schedule is sufficiently far for not to be in an adiabatic condition, then in general, all that I can say is, of course, this, which is, an average. If I imagine repeating the process many, many times according to the same schedule, I will get a result that is event dependent. And this average, all I can say is that this will be larger than negative T delta S, the entropy change, plus delta U, because delta Q is equal to T delta S only for a reversible process, right? But in general, this is smaller than that for a generic irreversible process, right? So in general, all that I can say is basically a statement that is an inequality between the work and the free energy change. And that's where thermodynamics, we learn in first year, stops. It sets a limit to how much energy change, free energy change I can extract from work, or vice versa, how much work I can extract from a free energy transformation. That's basically the famous limitations for the perpetual motion or the perfect machines that come from thermodynamic transformation. Okay? Now, what Jasinski and Crookes do, they go beyond this and they establish a relationship between a non-equilibrium, the work done in a non-equilibrium process, and the change in free energy. An equality, not an inequality. So what Jasinski theorem is saying is this incredible result. And I would like you really to appreciate how this is a remarkable result. So I want to indicate A and B to denote there is a direction here. I have a state A, say that the system has the proton is completely allowed to be relaxed. There's 0 endpoint distance in first approximation because the molecule is very small. And a final state in which, say, the molecule is fully stretched. And I can associate a change in free energy between these two states because these can be defined as equilibrium states. But I'm going from one to another in a collection of non-equilibrium events, and I perform the average of these collections of non-equilibrium processes. And even though I'm doing non-equilibrium transformation, what Jasinski is telling me, quite remarkably, is that I can get an equilibrium state function from non-equilibrium process, from a collections of non-equilibrium process. So this is non-equilibrium. And this is an equilibrium concept, thermodynamic concept. So you can get thermodynamics from non-equilibrium. How remarkable is that? Well, it depends how much you love statistical mechanics. Because if you do, you'll find it remarkable. Now, Crookes' theorem says something that apparently is a little bit less transparent, but turns out to be equally important, if not more. So what Crookes' theorem says, let me consider a forward process in which I go from, say, lambda 0 to lambda final according to some schedule. And let me consider, guess what? The reverse process. So we are putting ourselves exactly in the same framework of previous lectures. Actually, I used Jasinski Crookes theorem to lay down the discussion of second principle of thermodynamics I gave you last week. So it's not by chance that I see a connection with last week's lecture. But say I have the forward process and the backward process. And just as we did yesterday, Thursday, let me compare, so the process, in any time I realize some forward process or backward process, I have an entropy production associated with it, right? Now, the probability of producing some entropy delta S in the forward process divided by the probability of producing negative entropy in the backward process. I'm going to write it and then comment on it. This is the exponent of the probability delta S of the entropy divided by KB. So what am I saying with this? That anytime I do my forward process, I will generate a certain amount of entropy. And anytime I do my backward process, I generate some amount of entropy. Now, it turns out that if you remember how you define entropy in terms of heat, and therefore you express your heat in terms of, remember, Dex naught grad U, remember that? It turns out that the entropy production in the forward and backward process are related by a sign. If you walk along the same trajectory, but on reverse time steps, entropy production changes sign. Okay? Well, you can imagine this. Suppose you have a particle that drops down by gravity in your coffee cup. Of course, it hires the entropy of the bath. But if you go along the opposite process, it lowers the entropy of the bath because you never see a particle sucking up. So entropy changes sign under time reversal. Now, this cycle of relationships tells me basically this is nothing more than a revisitation of what we did last lecture. However, it has implication. One of the implications that it has, it allows you to prove Crookes theorem, Jasinski theorem very easily. And so the way you prove Jasinski theory from this is, so this is Crookes. So let me first assume Crookes and show you how Crookes basically gives you Jasinski. So the idea is to perform an average of this quantity of the entropy production along many forward processes. So start from here, many, many times. So how do I write this? Well, this is the probability that in a forward process I produce a certain amount of entropy. I integrate over this probability density from minus infinity to plus infinity, and I average the quantity that I'm averaging, because this is the density that defines the average, and this is the integral over the density. I'm just applying the definition, okay? Now, at least in the framework of Langevin dynamics, using exactly the arguments that we used last time, you can show that this can be written as the probability of observing the opposite amount of entropy in the reverse process. Why? Because remember, because of this fact, right? So this is nothing but a normalization condition. So I have this relationship. So what I was saying is that basically Crookes theorem implies that the average of e to the negative 1 over kb delta s over many forward processes, this is 1. Okay? But now I'm done, because now let me write this explicitly. 1 is equal to manage average over many forward processes as B minus SA. I'm calling B and A the final initial states. Now I'm using the definition basically relating the created entropy. So basically I'm saying that the work minus the free energy is the entropy produced, right? Do you agree? So since the work minus the free energy is the entropy produced, which tells me that if I'm in an irreversible process, there is a finite difference between the work and the change in free energy, then this can be written as the average of e to the negative beta, the work from AB, minus the change in free energy from AB along the forward process. Okay? But now I recall that the free energy, the Helmholtz free energy, is a state function. So it does not depend on the path. It depends only on the initial and final condition. Therefore, can be taken out of this average because it's the same for every realization. And therefore, I get e to the negative beta FB minus FA, the change in free energy, equals the averages of the work along the forward process. So we have just finished saying that basically we have proven that this ratio of entropy production in the forward and backward process, given the Crookes theorem, imply Jasinski theorem. So what we need to do now is to prove this relationship defined in the Crookes theorem. And this is the easy part of it, because we basically have done it. So if you go in the notes, you will find all the detail of the proof. But basically, it is just the same proof that we did the Thursday, repeated twice. So basically, what do? We look at the process, we look at the probability to observe a certain path forward in time. Let me call it plus t. This is a path. Given a certain schedule of the force that goes forward in time. With this notation, I'm referring to the fact that I'm looking at the famous forward process in which my, I go from initial to final in the positive schedule, and I compute the ratio with the probability of observing the reversed process given the time reversed schedule. Exactly the same ratio we calculated last time, right? Well, probably the numerator and denominator might be inverted, so up to an overall sign in the exponent, okay? Now, if you remember, the entire proof that we did last time was based on the fact that we could relate this to the heat, so that this guy was actually the heat of the forward process in the forward schedule. Again, this was a functional of the path. And now, if you remember, we could relate that this in addition to this heat, there was entropy, that this heat was associated with the entropy change in the bath. But along with the entropy change in the bath, there was also entropy change in the state of the particle, remember? And therefore, the total entropy produced in the forward process, for instance, will be KB. Now, I'm going to use a slightly different notation from last time. Let me just write it, and then I will comment. So the only difference with last time is that instead of using a time interval from 0 to t, here I'm following Crookes, and I'm using from minus tau to tau. So this is the change in the entropy of the particle, of my state. And of course, there's the change in the entropy of the bath, which is associated with the work, with the heat exchanged between the bath and the particle. So this is the entropy produced along my transformation, exactly as we did last time. Nothing more, nothing less. Now, if I now recall that the heat is an odd function of time, then basically what I must conclude is that the entropy produced in a forward process must be the negative of the entropy produced in the reverse process, which is basically equivalent, because the Q is an odd function of time, to say by this equation, Since I know this is odd, then I have a relationship between these two probabilities. So basically, this is equivalent to saying that the probability of observing X at the end of my process is the same as the probability of observing the initial configuration at the beginning of the reverse process. Or in other words, that in my situation, I go to a final configuration, and in the reverse process, I start from the final configuration and go back. And this is certainly true, this probability are certainly equal if the system is left to equilibrate at the end of my process, or if it starts at equilibrium in the reverse process. So basically, I'm doing something like this, guys. Let me see if I can show you. I don't know, two values, lambda final. The change occurs over a final window, then the system is left to equilibrate before and after. Then if I pair everything together, I get that the probability of X minus T times X of T given lambda of T divided by the probability of X bar at tau P of X minus T lambda minus T, which is exactly the ratio we computed last time, is the change of entropy of the forward process. So basically, you can skip everything we said up to now and start from here if you're taking last lecture, because last lecture was basically proving that this ratio here was the total entropy produced, so that if this ratio was 1, there was no entropy produced, right? So I'm basically recovering the proof of last lecture, nothing more, nothing less. The only difference is that the slightly different wording, in the second discussion, I was closer to Crookes' paper, while in the other discussion, I was more like closer to the Langevin dynamics language, and I was more pre-digesting that for somebody coming from path integrals and Langevin. But this is exactly the same ratio, and not surprised, we get that the ratio of this probability is exactly the entropy produced. And then basically we are at home, because all we need to do, the probability of generating some entropy in the forward process, I define it as the average over many independent processes. In each independent process, I generate some amount of entropy, and I average over many forward processes, and this will give me the distribution of entropy production in the forward process. And what is this? This is the integral over the initial configuration, the integral over the final configuration, the path integral from the initial to the final, the path density in the forward process, times the delta function, by definition, times the probability of finding the initial position at the initial time. This is the path density. And now you apply the ratio that we just demonstrated, the same ratio of last time, and this becomes sorry. Oh, shoot. the path probability of the reverse process, times the probability to find at the beginning of the reverse process xi, and then the delta function. But now, rather than writing negative delta S of the forward process, let me write delta plus of the reverse process. And then in the end, this is nothing but e to the 1 over kBt delta S PR negative delta S. Now, it might, I mean, I agree with you if you think it's a bit difficult to follow, because it is difficult to follow this demonstration the first time you saw them. However, I think I was paying quite a good deal to report each and every step in the notes, so that if you follow that, you should be able to recover this proof. But basically, so the key to understand all this is to understand the famous ratio R. The ratio R, or forward versus backwards, is equal to the change in total entropy, which is exactly of the forward. This is exactly the relationship we demonstrated last time. So once you have this under control, then basically you have everything, all the ingredients you need to prove Crookes relationship. And once you have Crookes relationship, you have Crookes relationship, you have Jasinski relationship for free. So in Jasinski process, one wants to understand the free energy difference between two states. And the way to do that is to repeat many transitions and to average. In Crookes process, one looks at forward transition and then backwards transitions, forward transition and backward transitions, and averages the ratio of these processes. So the ratio of the heat or the work done in forward and backward, and the result is related to the free energy differences between the forward and backward states. So these tools have been used by experimentalists to estimate the difference in free energy of macromolecular systems, literally by doing these experiments. By doing what is called pooling experiments, people were able to say that, you know, the free energy difference between a protein in the unfolded state and in the native state is that many kilocalories per mole, by measuring the work done to stretch it, which is something you can do because you know the force and you know the displacements. So by measuring how much work you need to apply with your optical tweezers to unfold a chain, and doing this many, many times, you get actually, in the end, an estimate of the difference in free energy, which is, if you want, an estimate of the stability of a macromolecule, for instance. And you know, it also means, if you know the difference in free energy of two states, you know the difference in the frequency in which these two states are realized at equilibrium, right? So for instance, suppose you want to ask yourself, suppose I have just to give you an idea of the implication of all this. Suppose you are in a situation in which, you know, you have a free energy, this is my lambda parameter, And these are now free energy, A F of lambda. And maybe with this free energy, I can distinguish between an unfolded state and a folded state, right? Because there are two minima of the free energies. These are two stable thermodynamical states, metastable states. And you know from Boltzmann that the difference between these two states is the relative population fraction. So you may ask yourself, how do I know how many proteins in an ensemble or in a glass are folded at any time and how many unfolded? Right? So in order to reply to this, you should look with your glasses with a microscope and count the proteins that are folded and unfolded. This is not something you can actually do, right? But what you can do is to take a protein and apply a force and unfold it many times, measure the work, and in the end of this many process, you average, you get a difference in free energy. And that difference in free energy is precisely the ratio of population. So you see how powerful this is? By doing, we translate a question that is in principle unanswerable, whatever this word means in English, not sure it exists, to something practical, to a procedure you can follow to get a result. Okay? I want to emphasize a little bit more what do I mean by state free energy as a function of a parameter. So let's suppose I have a function. So I want to introduce the concept of potential of mean force. So let's suppose that lambda, or whatever, let's suppose there is a function f of the microscopic coordinates that defines some macroscopic parameter gamma. For instance, gamma could be the endpoint distance of the chain where I applied my tweezers. So gamma could be the root of, say, the last amino acid or the last monomer negative the first monomer squared, right? In the multidimensional. This is really, that's an example. That would be graphically this would be like this distance. Now, in my condition, in my experimental condition, I might decide that, I'm interested in the states in which these endpoints is given by a particular value. So what do? I take my Boltzmann average over the microstates, and I'm putting a delta function that selects only the states that corresponds to a particular value of this distance, 25 nanometers, for instance, right? Now, clearly, this integral gives me a different value depending on what is the value of gamma I use, right? Now, I set this equal to negative beta g of gamma. So I interpret this as basically a thermodynamic state, and this is the Helmholtz free energy of that thermodynamic state. And this is called the potential of mean force. So this is what I mean by the free energy of two states defined by a parameter. For instance, the endpoint distance. That's the quantity that is accessed by the Crookes theorem. Okay. This part is admittedly difficult. Even though the concepts are all classical, the physics behind it is not completely familiar. At least it wasn't for me. And perhaps this is partially the reason why I find this difficult to teach a little bit. Because at least in my education, thermodynamics and statistical mechanics lived in parallel universe until this moment. So I find it difficult to convey this information in a clear manner, in a clearer manner. I find it much easier to tell you mathematically what is a Ito formula. You see what I mean? Because that's what it is. There's nothing to understand. Here, there's a lot of concepts to go back and revisit and try to digest. So what I recommend to you at this point is, okay, go back on the notes that I just uploaded a few hours ago. Try to follow them. And if we get stuck, we get a lecture and we try to address these issues together. Okay? Okay. And that was the last topic I wanted to touch on as far as thermodynamics and dynamics is concerned. And now I would like literally change subject. So what I recommend now is I take a couple of minutes break. We don't go beyond 6:30 because of we had an agreement with you guys that we would not go beyond a certain time because people had to leave. We will have a 5 minutes shorter lesson, but I want to give you the time to sort of relax your mind for a couple of minutes, or else the next lecture, which is on a different subject, will be very hard for you. Okay, so let's give you a couple of minutes, and then we start with a new subject. Okay.
Okay, thank you.
And the gap between these two is the gap between these two physics processes is essential, because if you place your cutoff within the gap, then you are interested in the physics much softer than the cutoff. Then you can exclude all the details of this physics and channel it through effective interactions that appear in the short distance, in the infrared sector. Remember? And all the spirit of that approach was that physics of the ultraviolet sector is not the details of the ultraviolet sector physics is not essential to describe the infrared physics. Now, this applies to pretty much everything in physics. And I went as far as saying that with very, 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 very few exceptions, physics starts when you can do this. Because if you have a continuum of state, doing physical modeling, it's basically impossible. Or stated differently, that's not a place where you should put your cutoff. You're not in the condition to write a theory anytime you increase by a small amount your energy of your resolution and new degrees of freedom pop up, right? Because how can you write an Hamiltonian if the Hamiltonian depends on degrees of freedom that vary with your energy? You have to wait until all of your particles, all of your relevant energies are covered before you can write a model, right? Now, let's now apply all of these ideas to the stochastic dynamics we have been discussing over the last several lectures. And in particular, we go back on a typical set of systems that we had already discussed and talked about. And it's a rugged energy landscape. So an energy landscape, I'm going to here represent it with 1D. Is said to be rugged or rugged anytime it has many minima and maxima separated by value. Now you can think about this in many dimensions, not only one dimension. Now I was careful enough to represent energies of different magnitudes. There's small energy barriers, and at least in this plot there are intermediate energy barriers, and there are large energy barriers. And you can complicate this at your taste, right? Putting any intermediate degree. Now, we have already had this discussion relating the height of energy barrier with the relaxation scales of the system, right? Now, of course, the question you should tell me is how now large and small compared to what? And the answer is compared to the thermal energy. I don't even have to ask you, right? So, for instance, if my thermal energy is this, there are only two types of barriers in this plot, the intermediate and the large, because these small corrugation are invisible at this thermal energy. Okay? Conversely, if my thermal energy is very cold, very slow, very low, then I have even these processes are thermally activated. And in this case, I expect my relaxation scales to be characterized by three main gaps, right? So I will have very fast dynamics associated with relaxation with the smallest basins. And this will be of the order, remember, of the entropy of these small states. We had this exercise already in the 1D example of the harmonic oscillator, remember? Then there will be a gap, and I will have thermal relaxation within these states. These are relatively faster processes, slower processes compared to the local relaxation within each of these states. Because there's a little bit of thermal activation of the order of delta U over KT, right? Crossing any of these barrier will take a time that is exponentially long in this height. So if this barrier is just a couple of KT, this will be a factor 10 of the microscopic relaxation time scale. So in log scale, this will be 1 order of magnitude. If this is 100 KT, then you can obviously see how many orders of magnitude separation of scales there would be, right? Now, along with this, there are even longer relaxation time scales. And then, of course, eventually now, how many gaps you have depends on how many, what is your thermal energy, so how many different kind of barriers you have. And you might be in a situation where you have barrier of any height. say, a dense spectrum, because your distribution of hyperbarriers is basically uniform in units of KT. Well, this is a kind of a glassy situation that you don't want to be in, because there's no gap. Dynamics at all scales is not good for theory. We have discussed that. Well, if this is the case, there's no simplification other than very small ones that I'm going to tell you, and you're in big trouble. But let's not assume that for a moment. Let's assume that there is at least one gap. So the simple situation on one gap is typically the typical barriers are all of the same height, more or less, in terms of KT. And there is no significant corrugation. Of course, probably this may be a little bit corrugated, but the KT is such that you don't see this corrugation. Okay? So in this case, I have fast equilibration mode within the states and slow interconnection among the states. Okay? And I consider this situation for sake of simplicity without loss of generality. Because if I want more complex system with, say, 2 hierarchies of barriers, I can always sneak in another set of states here and repeat the things that I'm going to tell you in a systematic manner. Okay? But for the sake of simplicity of my discussion, let us consider here a case of a single gap. Now, of course, if I have a single gap, now I'm in a good situation to do RG. I can sneak in a cutoff here. I call it lambda now. So this is the typical frequency or inverse timescales which sets my ability to resolve physical process. I will not be able to resolve timescales smaller than 2 pi over lambda. Okay? Now, what do they mean physically if I have only 2 barriers? So let's suppose we have, say, 3 states and 2 barriers for sake of simplicity. Okay? You heuristically, you imagine already 2 relevant frequencies to be around. This frequency, rate of transition of this barrier, the rate of transition of this barrier. Okay? So, and on top of that, there's also the zero frequency, which is the equilibrium distribution. Although this is a purely empirical description, no mathematical proof yet, you would imagine that in the spectrum there is the ground state and perhaps 2 more slow frequencies of some sorts. And then a bunch of high frequency modes associated with relaxation modes here, right? So sneaking my cutoff in the middle of this gap, it means that I'm neglecting the details of the local relaxation dynamics. The dynamics at the time scales of the local relaxation in harmonic oscillator with this energy scale. And I'm only focusing on the global relaxation dynamics. Okay? Now, if I were to picture this in a cartoon, let me do a 2-dimensional cartoon now. Let's suppose my energy landscape has beside 2 minima and separated by, sorry, 3 minima separated by a valley, right? So let me represent the minima with these basins and the valley like this. That means that, you can think about this as, here's okay, how do I say that? Okay, in Trentino language, say this is Trento, this is Arco. Sorry, this is Trento Rovereto, there's no barrier actually. So this could be Riva. Because you have to go through a little bit of height in the Bondone if you want to end up in Riva, right? And then between Riva and Rovereto, there is another little mountain. Of course, in the reality, Trento and Rovereto are on the same manifold of minima because they lie on the same valley. But let's pretend there is not, right? I mean, otherwise things get complicated. Okay. So now suppose you have a Brownian particle here. You start from here. What you will do, you will immediately end up exploring this state. Occasionally, you're going to venture and come back until you get a fluctuation that take you here and will take you here. You're going to visit the state, explore it, venture. Sometimes you come back here. Sometimes you get back here. You eventually end up here. And then ergodically continuing to doing this transition. So the sense of this discussion is that I am not interested in the local motion within the states. All this first dynamics is not anything I'm interested in. It's fast dynamics. All I want to do is a lower resolution in which I have my states, 1, 2, 3. I give up describing whatever goes on within the states. I only take the average collective properties of the states, assuming they are locally equilibrated. And I'm interested in the rate of transition between these states. So my description of the system in this representation will be, so this is time, and it's going to be left, 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 center, center, left, left, center, center, right. And all these are finite time intervals. So this would be like left, left, center, 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 left, center, right. Okay? This is the microscopic description. This is the state description. So under certain condition, I will be able to go from the Langevin equation, which I'll take for simplicity to be overdumped, to an equation involving the change in the population in time, or the rate of change in time of the population of the eth state. In this case, E is going to be left, center, and right. And this, under certain condition, will be given by a matrix that is called the rate matrix of the population, multiplied by the population vectors of population. This is called the kinetic equation or master equation. And then we will derive that under certain conditions. I'm just presenting, laying out our scope. Okay, so this is a matrix. This is a vector of states. And the vector defines the instantaneous population, the instantaneous probability of being in any of the states. And this equation will give you the dynamics in terms of probability in being in any of the states at a given time. Okay? And as you can see, the system depends on a matrix of parameters. And this set of parameters parameterize the ignorance concerning the microscopic dynamics. These are the effective couplings in the rigorous effective theory. All the details of the ultraviolet physics goes into these effective couplings. And the result is a simpler description of the soft physics. So in the analogy, these parameters plays the role of the monopole, dipole, quadrupole terms in the multiple expansions. And everything else are the dynamical degrees of freedom. Okay? Now, the goal of the next 2 lectures will be to establish this connection. That is, to start from this and somehow build a connection network that logically take you from these microscopic descriptions to the macroscopic description. And we will be relying on some mathematical theorem of stochastic processes that I will not demonstrate. I will state. These theorems have been demonstrated in the mathematical literature very, very recently, just like 15 years ago or something. Yet, they provide a definition of a state in thermodynamics. So something as fundamental as the concept of a state relies on theorems. One second. Sorry, my kid. Relies on concepts that have been demonstrated very recently. So let me just state what this theorem says. Okay, and then we pick it up from here next lecture. So suppose we have a Fokker-Planck system. So I have a Fokker-Planck equation. Suppose I have a spectrum of the Fokker-Planck equation with a numerable set of eigenstates, of course, potentially infinite. And I assume there is a gap, at least one gap. So I assume there are m eigenvalues below the gap. Okay, so fast modes, gap, and m eigenvalues. One of them is trivial, lambda equals 0, but m minus 1 are non-trivial. Okay, now clearly let LL be the set of right eigenmodes associated with these m states. I number them from 0 to m minus 1 to remind myself that the first one is trivial. Okay, now the mathematical theorem says something which sounds very abstract, but then physically can be easily interpreted. Okay, so what does the mathematical theorem is that using these right eigenvalues, I can always find exactly m linear combination Let me call it PL of x, k from 0 to m minus 1 of some coefficient L k of the right eigenmodes k of x. Now, the indices. This letter L labels one of these m linear combinations. For instance, L equal 1 is the first linear combination. L equal 2 is the second linear combination, okay? K runs over the right eigenmodes below the gap. The coefficients will depend on the mode, but also on the combination I'm looking at, because I have different linear combinations, not just one linear combination. So in particular, the first linear combination will have C1, the second linear combination will have C2, and so on and so forth. Okay? Now, what the theorem says is that I can always find such M linear combination such that the function PL of x satisfy with exponential accuracy, so up to terms that are exponentially small vanish exponentially with the temperature in the low temperature limit. Okay, I can always find exactly M linear combinations of such that these functions are positive, definite. So locally Gibbsian, meaning that in some neighborhood, this is some functions times the potential of my system around some points, not everywhere, locally, in the vicinity of some point x naught of configurations, in some region. Within that region, they are basically Gibbs factor. So I want to say to the locality, I want to enforce it through a characteristic function that is 0 outside this region and 1 inside this region. And there are L different characteristic functions because they could be Gibbsian around different points. And third property, disjoint. That means integral dl. If I integrate the characteristic, or if you want, the characteristic function of two different states is 0 up to exponentially small corrections in the temperature. Okay? So what these three sets of state, three set of conditions, the positivity, the local Gibbsianity, and the disjointness means is something that we will explore next time. And we will connect to physics. At the moment, let me just state them as mathematical facts. Okay? At the beginning of the next lecture, we will retake these definitions or refresh them, and then show that these mathematical results is basically the foundation of the idea that if I have a system, I can define local Gibbs distributions around each of these systems and consider the transition between locally equilibrated states. You see, these PL are basically locally Gibbs distributions around states. So the mathematics of this will imply the concept of local equilibrium. Okay? But we'll see this next time. Okay. Thank you I think I'm done. I'll see you Thursday. Okay.